Hello, everyone, and welcome to another session of Actuarial Statistics. I'm Eunice Frimpong from Accra Technical University. Today, we'll continue with our series on insurance statistics, and our focus will be on another important concept, unreimbursed loss. Now, by the end of this lesson, you should clearly understand, one, what unreimbursed loss is, two, how it is calculated. Three, its relationship with the insurance payment and total loss, and how we use it in actuarial science to model and manage risk. So what is unreimbursed loss? Let's start with the definition. The unreimbursed loss is the portion of the total loss that the policyholder, that is the insured, has to pay from their own pocket. We usually denote this by the symbol Z. The value of Z depends on the deductible, which we already discussed in our previous lecture. So mathematically, the unreimbursed loss is defined as Z equals to X, which is the loss amount, when the loss amount is less than or equal to the deductible, or Z is equal to the deductible when the loss amount is greater than the deductible. In other way of notation, we can say, in a more concise way, Z is equal to the minimum of either the loss or the deductible. So amongst these, with these two numbers, that is the loss and the deductible, if the loss is smaller than the deductible, then the Z is equal to the loss. But if the loss is bigger than the deductible, then Z is equal to the deductible. So we have X being the total loss, D is the deductible, and Z is what the insured pays. So if the loss is small, less than or equal to the deductible, the insured pays everything. And if the loss is larger than the deductible, they pay just the deductible. Let's interpret this further. If the loss is small, let's say 300 cedis, and the deductible is 500 cedis, then the insurer pays nothing, and the insured pays the entire loss of 300 cedis, because the loss of 300 cedis is less than the deductible of 500 cedis. Put water all over here. Hey, thank you for the water. Oh, I forgot about it. However, if the loss is large, say the loss, which is equal to X, is 2,000 cedis, and the deductible is still 500 cedis, then the insurer will pay Y equals 2,000, the loss, minus the deductible, which is equal to 1,500. So if the loss is large, say 2,000 cedis, and the deductible is 500 cedis, then the insurer pays 1,005 and the insured pays only the deductible of 500 cedis. So in every case, the insured pays either the full loss or the deductible, whichever is smaller. This structure ensures that the insured always shares some responsibility unless the deductible is zero. It discourages small claims and promotes careful behavior. Now let's introduce the expected value of the unreimbursed loss, Z, denoted by E of Z. This tells us, on average, how much does the insured expect to pay out of pocket? We compute it differently depending on whether the loss variable X is discrete or it's continuous. If X is discrete, we have E of Z equals the summation of X times the probability mass function plus the deductible times the probability that X is greater than D, given that X is less than or equal to D. Now, if X is continuous, we have E of Z equals the integral running from 0 to D of X times the PDF plus D times the survival function or the probability that X is greater than D. So we have SXD being equal to probability that X is greater than D. So note that fxx is the probability density function of the loss. And then SXD is the probability that the loss exceeds the deductible. This expected value is very important in understanding the insured burden in the cost-sharing arrangement. So here's an example to make it practical. Suppose the deductible is 1 and the loss X is uniformly distributed on the interval 0 to 10. X follows the uniform distribution 0 with a minimum value of 0 and a maximum value of 10. Then f of X, that is the PDF of the loss, is 1 over 10. And the survival function, that is the probability that X is greater than 1, is equal to 1 minus 1 over 10 and is equal to 0.9. Remember, the PDF of a uniform distribution is 1 over B minus A, where 0 is A and 10 is B. So 1 over 10 minus 0, giving us 1 over 10. Same for the survival function of the uniform distribution. So now compute the expectation of Z using the formula provided on the previous page. Then we have E of Z is equal to the integral of X times the PDF 1 over 10 dx plus the deductible D times the survival function at 1, which is 0.9 from here. And the integral is running from 0 to the deductible, which is 1. So we simplify this to get x squared over 20 from 0 to 1 plus 0.9. And we can further go on to work on this simplification. And we'll get a final answer to be 0.95. This means that on the average, the insured pays 0.95 units of the loss, even with insurance, because of the deductible. Now let's look at how the total loss is divided. The total loss X is shared between the insurer, who pays Y, and the insured, who pays Z. This gives us a simple but powerful identity where Y plus Z is equal to X. No matter what values Y and Z take, together they must add up to the total loss. From earlier lectures, we defined Y being equal to the maximum of 0, X minus D. That is, and we also defined Z as the minimum of X or D, which is the unreimbursed loss. So we can go on to say that Y plus Z is equal to the maximum of 0 or X minus D plus the minimum of X or D. And that should be equal to X. Let's verify this. If X is less than or equal to D, then Y is equal to 0 and Z is equal to X, which implies that Y plus Z is equal to X. And if X is greater than D, then Y is equal to X minus D. Then Z is equal to D, and which implies that Y plus Z is equal to X. So in both cases, the identity holds. This relationship is very useful when constructing models and also when checking if our computations are correct. Since Y plus Z is equal to X, the expected values also, so we say that expectation of Y plus expectation of Z is equal to the expectation of X. This is especially useful in actuarial models. It allows us to verify that our expectations for what the insurer pays and what the insured pays align with the total expected loss. However, note this carefully. The second moment of the loss is not equal to the second moment of what the insurer pays and plus the second moment of what the insured pays. That is, the variances do not simply add up the same way as the expectations add up. So this identity applies to expectations, not to variances or second movements. The question now is, why do we care so much? Or you might ask, why do we care so much about this identity? The first thing is that it helps insurers and actuaries allocate responsibility between the insurer and the insured. Secondly, it's used in premium pricing to determine fair costs for both parties. Also, it is useful in reserving, where insurers must set aside funds to pay future claims. And then most importantly, it ensures that the entire loss is accounted for. No part is missing. So understanding the relationship between X, Y, and Z gives us a full picture of how deductibles influence cost sharing and risk management in insurance. In conclusion, to summarize, unreimbursed loss Z is a portion of the loss the insured pays. It is calculated using Z equals the minimum of X or D. We compute the expected value Z to estimate the insured's average out-of-pocket cost. There is a fundamental identity, which is Y plus Z is equal to X, and it helps us validate our models. This identity also applies to expectation. Now, these relationships are fundamental to the design, analysis, and pricing of insurance contracts. Thank you for listening, and I hope this explanation helps you understand the concepts better. In our next lecture, we'll move on to policy limits, another key feature of insurance contracts. Until then, take care and keep revising.